Welcome to the seminar series. This is put on by the Computational Engineering Division. So the Bayesian and Frequentist divide within the statistics profession is of historic proportion, and it has relevance to both statisticians and non-statisticians alike. As scientists and engineers are having to grapple with ever larger quantities of data, statistics plays an increasingly important scientific role for data fusion, for uncertainty quantification, and ultimately for informed decision-making. An understanding of the historical approaches to statistics and probability is of interest to all of us who, as our speaker says, quote, employs, applies, consumes, or contemplates statistics and data analyses. Kristin Lennox has been at the lab since finishing her PhD in 2010 at Texas A&M University. She is both the founder and the current director of the Engineering Statistical Consulting Service. She has provided statistical expertise on a range of problems at the laboratory, involving everything from lasers to explosives. Please join me in welcoming our speaker, Dr. Kristin Lennox.
All right. Today I speak to you of war. A war that has pitted statistician against statistician for nearly 100 years. A mathematical conflict that has recently come to the attention of the normal people. And these normal people look on in fear, in horror, but mostly in confusion because they have no idea why we're fighting. I speak, of course, of that Bayesian versus Frequentist thing. Now, not too long ago, people didn't have to worry too much about the differences between different types of statistics. Some people didn't even know there were different types of statistics. That started to change in the 90s when this thing that we call Bayesian inference began to slowly creep its way in and infiltrate various areas of science and technical interest, but it was still something that you wouldn't just encounter in day-to-day life. No more. These days you can be minding your own business, reading the news, and all of a sudden, bam! Bayesian statistics happens. This is particularly common in election years. I blame Nate Silver. But, as so many of us do. But the reason this is an issue is because you're being presented with this information, but no one's exactly told you what to do with it. We live in an increasingly quantitatively sophisticated world, and people have access to tools for prediction and inference and understanding data that previously they would never have seen, which again would be grand if someone had ever bothered to tell you how they work. Now, this is not a uniquely Bayesian problem. Let's face it, most people view all statisticians as sort of a hybrid of an accountant and a wizard, which is ridiculous. We have nothing in common with accountants. But the fact remains, before I can explain to you the difference between different kinds of statistics, I have to first tell you what is statistics without qualifiers. And I like to call this the central dogma of inferential statistics. Statisticians use something called probability to understand and to quantify uncertainty. Now, this is not the only thing that statisticians do. Sometimes we draw pictures. But this is something that all statisticians do, and it's something that we all spend a significant amount of our time doing. And the statistical procedures that you have most likely been exposed to are this, or at least attempts at this. So if the underlying principles of statistics are this simple, where is there room for disagreement? And I'll give you a hint. We mostly agree on what probability is. So the place where you see conflict and divisions within statistics is this second italicized word, uncertainty. Probability is a mathematical concept. It is exquisitely well defined. Uncertainty is an English word. What it means kind of depends on when you hear it. So the central difference between Bayesians and Frequentists is what they mean when they say that they are quantifying uncertainty. So how am I going to explain this to you? Here's our little roadmap for the talk. Hopefully, you already believe that this is important. It matters that people understand how statistics works because, frankly, it's inescapable at this point, and you ought to know what you're expected to do with it since it's already there. I'm going to explain these two key concepts in my central dogma of inferential statistics. What is this thing called probability? This is mostly a vocabulary lesson. And secondly, what is this thing called uncertainty, or rather, what are these different things called uncertainty that different statisticians are trying to describe? I am then going to take you through a very, very abridged tour through the history of uncertainty quantification, which is the history of mathematical statistics and probability. The reason for doing this is because different people throughout the last several hundred years have used probability in different ways to solve different problems. And if I can show you the different styles of inference that people have been using throughout history, hopefully that will allow you to better understand not only what the Bayesians are, but the different styles of inference that you are presented with today. And finally, the big reveal. This is a highly partisan topic. One of the nice things about it is it's very openly partisan. You are never really left in doubt as to whether the person you're speaking to is a frequentist or a Bayesian and what their corresponding biases might be. So I have tried to keep this talk as unbiased as possible, but at the end, it's only fair to let you know how I feel about it so you can figure out where you should believe me and maybe where you should believe somebody else. So, moving along, what is this thing that we call probability? Probability, as we currently understand it, dates back to a 1933 monograph by Andrei Kolmogorov. And Kolmogorov's insight was that this concept of probability, which previously had been sort of isolated from the rest of mathematics, was actually a special case of something called measure theory. And what measure theory is the mathematical formalization of ways that we actually measure stuff in real life. So for example, there is a mathematical formalization of the concept of length. It's called the Lebesgue measure. There is a mathematical formalization of the concept of counting. It's called the counting measure because no one quite had the nerve to name counting after themselves. Different? Not after all this time. So different measures measure different kinds of things. The kind of measure that we apply to things called uncertainty is probability. And what makes it different from other measures is that it always takes a value between 0 and 1. So key concepts in understanding probability. Probabilities have to take a value between 0 and 1, which means if you take all possible outcomes or all possible things of interest, the probability of all of them together has to be 1. The way that you allocate those fractions of probability among individual events or sets of events is called a probability distribution. And there are a couple of familiar distributions, such as the exponential distribution there, which allocates probability across all real numbers. The normal or Gaussian distribution, which, exponential is all positive real numbers. The normal or Gaussian, which allocates probability across all real numbers. And there are also discrete distributions, such as, for example, the distribution over the outcomes when you throw a 6-sided die, which is a distribution over the numbers 1 through 6. So, statisticians define distributions according to things called parameters. When you have a named distribution, like the exponential or the normal, you can perfectly define it using a small set of numbers. So for example, with the exponential distribution, if you know the scale parameter, you know everything about that distribution, you can calculate any number that you want. Similarly, with the normal or Gaussian distribution, if you know the mean and the standard deviation, you can calculate any probability that you want. For our dice distribution, the parameters are the probabilities of occurrence for each of the 6 sides. The reason that you, as non-statisticians, should care about parameters is because this is what statisticians do inference on. So let's say, for example, I want to test a hypothesis about whether or not men who work at the lab tend to be taller than women who work at the lab. Well, I will define a distribution on the heights of men at the lab. I will define a distribution on the heights of women who work at the lab. But I'm not going to compare these big distributions head to head. I'm going to compare their parameters. I'm going to compare probably their means to assess whether or not my hypothesis is true. So parameters matter because they're the tools of inference that statisticians use in a lot of cases. I will sometimes have exceptionally bad notational manners and use the terms parameter and hypothesis interchangeably. I apologize, but hopefully now you'll kind of understand what I mean. Last key concept is something called the likelihood. Now, the formula that's up there is something called a probability mass function. It's a way of describing a distribution with parameter theta, and basically it is just the function that returns the probability that a random variable takes a value little x, given that the distribution has parameter little theta. And if I summed up over all possible values of little x, I get 1, because that's what probability distributions do. Now, what happens if I flip this function on its head? If instead of fixing my parameter theta and varying my data x, I fix x and I vary theta. That is something that is called a likelihood. So the likelihood is a key tool in both Bayesian and frequentist inference, and you can sort of see why that would be, where if you calculate the likelihood for a bunch of different parameter values, the ones that have a higher likelihood value are in some sense more consistent with your observed data than the ones with lower likelihood values. Something to keep in mind about the likelihood, though, is that it is not a probability distribution. Remember, when I was integrating over x, that had to integrate to 1. If I integrate over theta, that does not have to integrate to 1. It doesn't even have to be a finite value. And this is going to matter a little bit later in the talk. So, I'm sure you're relieved. That's everything you need to know about probability for now. Now, we're going to get into this more subtle concept. What is uncertainty, or what are the different kinds of things that statisticians would call uncertainty and try to describe with probability? This is a subtle concept, and I've been told that one of the best ways to explain subtle concepts is through the use of story. So I wrote you one. I call it The Statistical Lunch Bunch and the Summer Student Revolt of 2015. It is entirely fictional, yet strangely plausible. So once upon a time, there were 6 statisticians, and these statisticians worked together, and they played together, and they went to lunch together every Thursday. Now, there are 2 key things that you need to know about statisticians. The first, we are creatures of iron will. The second is that we are creatures of slight whimsy. Now, the iron will was really causing problems for this group of statisticians because they could never agree about where they should go to lunch. However, instead of taking turns, they came up with a more whimsical solution in the form of dice. So every statistician had a number, we rolled the dice, and whoever's number came up got to pick the restaurant. But these were not just any dice. Oh no. These are what are called precision dice or gaming dice, and they are exquisitely engineered to have equal probability of occurrence for all 6 sides. So when I say I am uncertain about where I'm going to lunch on Thursday, that is due to the inherent random nature of the outcomes of throwing these die, rather than any situation where I'm ignorant about the physical properties of these die. Now, one of these statisticians was a collector of dice and a connoisseur of dice, and was not entirely satisfied with the current lunch selection solution, mostly because the dice are kind of boring. I mean, they're mass-produced, they're plastic, they're also sharp, and they kind of hurt when you hold them. So she came up with a more whimsical and overall superior solution in the form of hand-carved ebony dice with hand-applied brass pips. Now, these dice add a certain amount of elegance and panache to any event where they are used, and she presented this alternative to her fellow statisticians, and they liked it, but they were a little bit concerned because they were uncertain that these dice were fair. So remember, with our blue dice, we know that the outcome probability for each of those sides is equal. For these dice, we do not actually know what the probability of outcomes are for different numbers because they are less carefully manufactured. So the mathematicians talked for a little while, and they decided that the increase in whimsy was acceptable as a benefit for the sacrifice in certainty. However, they did want to certify that these dice were at least kind of fair. And they came up with a testing procedure that basically involved rolling the dice 50,000 times and writing down the outcome, which is doable, but no one was volunteering. Fortunately, a solution presented itself in the form of our summer students. So we went to our summer students and we told them that they were going to spend their internship at a national laboratory rolling a die over and over and over again and writing down the outcomes. And we told them they were following in the proud footsteps of John Carrick, who was a mathematician interned in Denmark during World War II, who spent the period of his imprisonment flipping a coin over and over and over and over and over again to prove that the law of large numbers works. And he got a publication out of it. So this is a true story, and I personally find it very compelling. They didn't buy it. So they refused to help us with our little experiment, and we had a period of very tense negotiations while we were trying to figure out how can we figure out if the dice work while they have what they consider to be an intellectually satisfying summer experience. Apparently somebody told them that if you come to a national lab, it's all lasers and explosions all the time. But eventually we were able to come to a mutually acceptable solution in which they were going to leverage the fantastic computational capabilities available here at Lawrence Livermore to build an exquisitely refined physics model of our wooden dice so that they could simulate rolling them over and over and over again instead of doing it for real. There was just one tiny problem. Our summer students, like us, are statisticians, which means they had never built an exquisite three-dimensional physics model before, and we were uncertain as to whether or not they had done it right. So while we were discussing how we might validate their work, the entire situation was overcome by events in that the statistics group hired 2 new people. Now we can't use 6-sided dice at all. We need 8-sided dice. And you might imagine that a statistics group with a dice collector as a member might have access to an 8-sided die, or even a selection of 8-sided dice. You would, of course, be correct, but, we're back to mass-produced plastic, aren't we? Whereas there are alternative options, such as, for example, additively manufactured, custom-made 8-sided spinners available in a variety of attractive metals and finishes, which are just a wonderful way of making any 8-factor decision-making process more fun. However, one is uncertain as to whether one should bite the bullet and purchase this item because, on the one hand, I don't actually need it. On the other hand, all of my dice collecting friends will be extraordinarily jealous. So here's a form of uncertainty which is not tied to any physical process at all. It exists only in one's mind, and it describes a state of belief. So I've run out of space, which means that we're not going to talk about any additional kinds of uncertainty, and I leave you on the cliffhanger, did I buy the top? Of course I bought the top. But the point is, I have shown you 4 different kinds of uncertainty, not exhaustive, and all of these styles of uncertainty are quantifiable, and all of them can be described using probability. However, if I use probability to describe all these different kinds of events, clearly that probability is going to mean something different in different situations. And I'd say the 2 cleanest examples of that are going to be the blue dice and the gold top, where in the blue dice situation, we have an actual physical system about which we have exquisite knowledge, but we are still uncertain as to its next outcome. Now, this is a style of uncertainty that's called randomness, it's called aleatoric uncertainty, and when I use probability to describe this situation, it's called objective probability or frequentist probability. And the word frequentist refers to the long-range frequencies of random events. Now, on the other side, I have the gold top. The gold top is not tied to any physical system. There's not a right answer somewhere graven in stone. If I am using probability to describe my thought process on whether or not I should make this purchase, then that probability is entirely subjective. It describes a state of knowledge or a state of belief, and it could differ from person to person. Now, this is sometimes called subjective probability or Bayesian probability. So we have now laid out the 2 sides in our conflict. Most statisticians would agree that objective probability is the right way to describe the blue dice, and subjective probability is the right way to describe the gold top. It's really hard to get all statisticians to agree on anything, but most. But what about those middle 2 situations? In both of those situations, I have uncertainty about a real physical system. The wooden dice do exist. They have some physical properties. They have some distribution over their outcomes. So that's like the blue dice situation. However, I am ignorant on some level about how this system behaves. I could conceivably learn more about it. So in that case, I also have some subjective uncertainty about how these systems work. So when I say I want to use probability to describe those 2 intermediate systems, the frequentists say, well, of course, you should use objective probability to describe a physical system. And Bayesians say, well, you should use subjective probability to describe your state of belief, and then they fight. And so that's the difference between the Bayesians and frequentists. It really is almost a units problem, even though probability is unitless, where it can be used to describe 2 very different kinds of uncertainty. And to give you an idea of how we found ourselves in this point, now I'm going to give you a brief history of uncertainty quantification. How did we end up with different styles of probability describing different things? Going back to the beginning, what we consider to be the origin of mathematical probability today is a series of letters that were exchanged between Blaise Pascal and Pierre de Fermat in 1654. What were they writing about? Well, they were writing about gambling, and specifically something called the problem of points, which is the question of if you are playing a game of chance against an opponent and you are interrupted before that game is completed, how do you split the stakes? And this was a matter of great interest to both mathematicians and gamblers. And in the course of figuring out a mathematically rigorous way of addressing this problem, they came up with the core concepts that describe probability today. For example, Pascal came up with the concept of expected value, which these days means something like a mean or a measure of central tendency. Back then, it was literally the expected value you will get back when you place a bet on a game of chance. And this is what probability was. It wasn't even called probability back then. It was called the Doctrine of Chances, or the study of chances, because it was the mathematical description of games of chance, things like dice and cards and lotteries. And that's how things stayed for a very long time, with the first hint of broader application coming in 1763, when a publication came out that had been written by a gentleman by the name of Thomas Bayes. Now, Thomas Bayes was a Presbyterian minister, and he was also an amateur mathematician. He'd published in a variety of areas on different mathematical problems, but he had a very interesting idea about this doctrine of chances, which we now call probability, which is, how can you use probability to describe learning? How can you use it to describe an accumulation of information over time so that you can modify a probability based on additional knowledge? So since he was a Presbyterian minister, he wasn't going to talk about dice or cards or lotteries. He came up with his own thought experiment, which he did not bother to name, but which I shall, and I call it blindfolded one-dimensional table bocce. Bayes bocce for short. And this is a notional game setup. The way that the game is played is that you don your blindfold and you take in hand your starting ball. You're going to throw this ball at the table in such a way that it has an equal probability of landing in any location on that table, and your job is to guess where it is. If that sounds impossible, that's because so far it is. This is where your friend comes in. They're not wearing a blindfold. Now, you're going to take one of these secondary balls, shown here in blue. You're going to throw it at the table in the same way, and your friend is going to tell you whether it landed to the left or the right of the ball you started with. And as you continue playing this game for multiple rounds, you will learn where the red ball is. So what does this look like? Here's my Bayes bocce simulator. You can see the overhead view of the table. We've also got the side view because we're only interested in that distance from the left. And on the bottom, that is my starting probability distribution for the location of that red ball, where it is flat, because I threw it in such a way that I do not have an idea that it's in one part of the table versus another, and the true location is marked by that vertical line. So, round one. Blue ball fell to the left of the initial ball, and you can see I've updated my probability distribution. It's fallen to nothing on the extreme left edge of the table, gradually increasing the closer you get to the right. Round two. Two balls have fallen to the left. Now I have almost no probability on the left half of the table, again, increasing the closer that we get to that right edge. Let's skip ahead a little bit. Round 10. I've now had 9 balls fall to the left and 1 fall to the right, and I've got this peaky distribution, which is not centered exactly at the true location, but it's pretty close. Skipping ahead to round 25, we've now had 22 balls fall to the left and 3 fall to the right. And again, this distribution is becoming narrower and getting closer to the true location of the red ball. Now, trust me, if I kept playing this forever, eventually I would get something that's very, very closely centered around the true location of my starting ball. How did Thomas Bayes come up with this? And how am I doing those calculations for the probability distribution? Well, though Bayes was far too modest to say so, he used Bayes' theorem. Bayes' theorem describes a concept called conditional probability, which is the probability distribution of one event or random variable given information about other random events. So in this case, the event we're trying to get information about is X, the location of that red ball. Our ancillary information is the left-right information we have about the secondary balls. And you can see this is a function of the distribution of the left-right information for the secondary balls given the location of that red ball. That's just a binomial distribution. And that starting flat unconditional distribution for the red ball. So what is Bayesian about this? Remember, I said Bayesians are so defined because they use a subjective interpretation of probability. Probability as state of belief rather than description of randomness. So what's Bayesian about Bayes' theorem? Absolutely nothing. Bayes' theorem is a theorem, which means it works for probability no matter what your interpretation of probability is. If you want to be Bayesian with Bayes' theorem, then you need to take an additional step. So what Bayesians do is they use Bayes' theorem to perform inference about distribution parameters. Remember I said that's what statisticians describe. We talk about distribution parameters theta. And what they do is they calculate the conditional distribution of a parameter theta given the observed data x. So what makes this a Bayesian procedure? Well, it's got a couple pieces. The first is our old friend, the likelihood, where you're just taking a probability density or mass function, treating it as a function of theta rather than x. But then there is the prior. So the prior is the unconditional distribution that you put on that parameter theta. We do not necessarily think theta is random. Remember my example of a parameter earlier, the mean height of men at the lab. We don't think that's a random variable, we just don't happen to know what it is. So if I'm using probability to describe something that is not random, I'm not using objective probability, I'm using subjective probability. Probability as a description of a state of belief or a state of knowledge. You put all these things together and it's called the posterior distribution of theta given x. And again, we have our constant of integration because probabilities have to integrate to 1. It's the rule. So I've already told you Bayes' theorem isn't Bayesian. Was Thomas Bayes Bayesian? Well, we don't quite know. We do know that he never really applied his theorem to real problems. In fact, the paper describing it wasn't even published until after his death. So who was the person who took Bayes' theorem and did this with it? Who said we should be doing this subjective probability-based inference for scientific problems? And that gentleman was Pierre-Simon Laplace. Pierre-Simon Laplace was what you might call a probability enthusiast. He took this thing that was used to describe gambling games, and he said, let's just use it to describe everything. And he applied it to problems in biology and problems in sociology, to astronomy. He wanted to apply it to criminal justice, where he wanted trials in France to actually quantify the evidence and come up with some kind of posterior distribution of guilt or innocence at the end. That part didn't catch on. But the science parts did. And the reason was, up until this point, there wasn't really a quantitative way of accounting for uncertainty in data or models. And so this style of thinking, which we called Bayesian statistics, back then was called inverse probability, was the only game in town. Eventually, Laplace came up with something called the central limit theorem, which is a cornerstone of frequentist inference. So, the entire conflict really is his fault. But the central limit theorem only applies when you have large samples. And so during Laplace's time, and for over 100 years after that, the only way to do inference for small samples was using Bayesian statistics, basically. And some people hated it. And it's worth talking about why, because it's not like there was a better alternative available, and the issue was the prior. Some people just did not like this prior, they weren't sure how they were supposed to come up with it, and they really didn't like the fact that if two people came up with two different priors, you could get a different answer to the same scientific question. So here is an example that illustrates this that is actually one of Laplace's own. How do you calculate the probability that the sun is going to rise tomorrow? So first, we need some prior on the probability of the sun rising, and Laplace said, well, it may rise, it may not. Other than that, I don't know. So it's just a flat prior on that interval. We need a likelihood, and he said, okay, well, we're going to use as our successes every time the sun has risen in the past, which thankfully has been every day so far. And one of the confusing things about Bayesian statistics, at least when you talk about it, is that you're calculating probability distributions on probabilities. What we're actually going to call the probability of sunrise tomorrow is the expected value of this distribution over the probability of sunrise tomorrow. And it is available in closed form in this case. Trust me, I'm a professional. And is simply the number of times the sun has come up in the past, plus 1, divided by the number of times the sun has come up in the past, plus 2. Plugging in numbers, Bayes said the sun has risen every single day for the last 5,000 years, including leap years. And so that is his calculated probability of the sun rising tomorrow. 1 minus that, the probability of the sun not rising tomorrow, is about 1 in 2 million. That number is very small. It is not small enough. For one thing, we know that the Earth is over 4 billion years old, which means that if that were the actual probability of the sun not rising on any given day, we'd have had well over 2,000 sunless days by now. So not only do we not believe that number, Laplace didn't even believe that number. So when he was talking about the probability of the sun rising, that 0.9999, etc., he said, this number is far greater for him who, seeing in the totality of phenomena the principles regulating the days and seasons, realizes that nothing at the present moment can arrest the course of the sun. So if you ask some random person who doesn't know anything about the sun, this is their correct probability for the sun rising tomorrow. If you ask Laplace, he says, don't worry, it's coming up. How does this work? Remember, probability got its start describing gambling games. And the probability of rolling snake eyes does not depend on who you ask. Ideally, it also doesn't depend on who's rolling. But how do you make that leap from a description of physical phenomena, physical processes which are the same for everyone, to a situation where the probability of the sun coming up changes depending on who you ask? And the answer is, of course, this is subjective probability. We aren't talking about the actual probability of the actual sun coming up tomorrow. We're talking about our state of belief that the sun will come up tomorrow, which of course depends on what you happen to know. How did Laplace make this leap? How did he go from a description of random events to a description of a state of belief as the interpretation of probability? And why on earth didn't he tell people that that was what he was doing? Well, the answer is because Laplace didn't think he was making a leap at all. Laplace did not believe in randomness. It was actually pretty common during Laplace's time to believe that the world was entirely deterministic and predictable, and that if you just had enough knowledge of starting conditions and of the laws of physics, you could predict every event, including the roll of a die, going out into eternity. And it wasn't until the 20th century that we started to see scientific and mathematical revelations that made people start to question this. So to Laplace, the only kind of uncertainty there was uncertainty due to ignorance, was the kind of uncertainty you describe with subjective probability. Now, that being said, even though this is how he justified it, and this was literally the only way people had of sort of calculating probabilities for hypotheses, a lot of people didn't like it because, first of all, you have to come up with a prior, and second of all, if different people come up with different priors, particularly if there's not a lot of data, you can get different answers. So there was a real push to get the prior out of statistics the only way that you can, which is by coming up with a style of inference which is tied only to objective probability, only to randomness. And that is what the Frequentists did. So my two representative Frequentists are Ron Fisher, who came up with the concept of maximum likelihood and ANOVA. He was also very influential in coming up with the idea of randomization in experiments, and would not appreciate being called a Frequentist, by the way. He advocated a third style of inference called fiducial probability, but it didn't catch on, so we'll just leave him up there. And also we have Jerzy Neyman, who along with his partner in crime, Egon Pearson, came up with the decision theoretic foundations of frequentist hypothesis testing. So this idea of controlling your false positive or type 1 error rate and then minimizing your false negative or type 2 error rate and using that to define an optimal test, that was due to his work. So these gentlemen and a variety of other people who founded frequentist inference did something very interesting. They came up with a way of doing probabilistic inference which is tied only to randomness. It doesn't have subjective probability at all. And as you might imagine, there are some caveats to this and some limitations on it. And the best way for me to explain them to you is by showing you a particular inference problem, doing it as a Bayesian, and then comparing that to how you might approach the same problem as a frequentist. So let's go back to our statistical lunch punch and imagine we have decided to use the wooden dice, and I have been assigned the number 1. Remember, we don't know if these dice are fair, so I want to make sure that they're at least unfair in my favor. So I do a little experiment. I roll the dice 50 times, and I get 12 ones, which is a 24% success rate. That's better than fair, which is closer to 17%, but I know I have not fully characterized these dice. So I want to know, okay, what is the lowest reasonable value for this probability of rolling a 1, which I'm going to call theta from here on out? And I'm going to say, well, I'm willing to accept an uncertainty of 5%. Weasel word is used advisedly because uncertainty is going to mean two different things over the next 2 minutes. So first off, I am a Bayesian. So the first thing I have to do is pick a prior, and that prior that you see up there is called the Jeffreys prior. Turns out that's a better way of expressing ignorance of a proportion value than just a flat prior. Now I'm going to calculate my posterior distribution using my 12 successes and 50 trials, and I get something that looks like that, nice peaky distribution centered around 0.24, and I say, this is my probability distribution for theta, find the 5th percentile, and say, with 95% probability, the probability of rolling a 1 with these dice is at least 15.3%. So far, so good. Now, I put on my frequentist hat, and I can't do any of that anymore. Remember, as a frequentist, I can only describe random events or events that are similar to random events using probability. So what was random in that problem I just described? Well, the only thing that was random was the experiment, where I rolled the dice 50 times. Unfortunately, it's not random anymore. I already did it. But can I come up with a procedure that if I had 100,000 dice and I wanted to come up with an interval for each of them by rolling it 50 times and counting the ones. Can I come up with a procedure that is going to work for 95% of those random experiments, which is called a 95% coverage probability? And it turns out you can, and that is called a confidence interval. And I don't really have time to explain how it works, but this is how you calculate it in this case. I'm going to figure out what outcomes of my hypothetical experiment are as or more consistent with values in my interval as the one I saw. In this case, that means anything that produces 12 or more ones out of 50 trials. So now, I'm going to take every possible theta, every possible probability of rolling a 1, and I'm going to calculate the probability of getting 12 or more ones out of 50 trials. And that's what that looks like. That is not a probability distribution. That is just a probability calculated for a bunch of different values of theta, which is varying over the x-axis. I'm going to identify all of the probabilities up there that have less than a 5% chance of producing 12 or more ones, and I'm going to boot those out of my interval. And the reasoning behind that is because if I really had a probability that small, I don't think I would have gotten the data that I actually saw, which was exactly 12 ones. And then I can say, with 95% confidence, the probability of rolling a 1 is at least 14.5%. And this procedure does, in fact, have that 95% coverage probability, which is to say, for 95% of experiments that you carry out this way, the interval will capture the real parameter value, but of course, you don't know if you've captured it for any particular experiment. It's worth pointing out I pretty much got the same answer twice. I mean, both of them say that the probability of rolling a 1 is greater than 15%-ish, with uncertainty, whatever that means, of 5%. It was a lot harder to explain how the frequentists did that. And I would like to leverage my experience in teaching frequentist statistics to tell you it takes a very, very long time to get people to understand where probability comes into play in frequentist procedures. That you have this coverage probability for a confidence interval, that when you're doing a hypothesis test, you do not actually have a probability that the hypothesis is true. Bayesian inference can give you that, but frequentist inference can't because a hypothesis is not random. A parameter value isn't random. And it takes a while to sort of wrap your head around that, and that is one of the primary Bayesian critiques of frequentist inference. So why did this catch on? And boy, howdy did it ever catch on. The advent of statistics as being a key piece of the toolkit for science really was the advent of frequentist statistics. They're much better at marketing than the Bayesians. And all of a sudden, even though objective probability it's inflexible, and it requires these sort of ancillary randomized experiments before you can calculate results, you've gotten rid of this problem of the prior, which is twofold. The first is, how do I come up with a prior that really represents my beliefs if I'm not a statistician and I therefore don't think in probability? And second of all, how do I deal with this situation where if I have one prior and you have a different prior, we get different answers? Oh no. So by getting rid of the prior, they got rid of this problem, and they put statistics in the hands of people who don't think in probability. Now, this made statistics enormously popular. It's also led to a lot of the problems that we're experiencing in statistics today with misinterpretation of results. If you want my take on frequentist statistics, please see my other talk, Everything Wrong with Statistics and How to Fix It, now available on YouTube. But rightly or wrongly, when this caught on, the Bayesians had to find a way to respond to it and to respond to the implicit critiques of Bayesian inference that were sort of embedded in the popularity of frequentist inference. And you'll be shocked to hear they couldn't agree on how to do that. So there is one school of Bayesians, I'll call them the subjective Bayesians, who just doubled down on subjective probability. They said using these ancillary randomized experiments is silly when you can just directly use probability to quantify your state of knowledge for an experiment. But they did pay attention to the critique where it's hard to come up with a good prior when you don't think in probability. So they invested a lot of effort and a lot of research time into figuring out how do we do that better? How do we really represent people's state of knowledge using a probability distribution? And they came up with a concept called expert elicitation, which is how do you pair up someone who thinks in probability with someone who knows about science and find a way to write down a state of knowledge of science using probability. Some subjective Bayesians took it a little bit farther, and they denied the existence of objective probability at all. Probably the most famous of these is Bruno De Finetti, who liked to say probability does not exist. He did not mean mathematical probability. He meant that probability is not representative of any real-world phenomena. It was sort of a callback to Laplace's view. The only reason we can't predict things is because we're ignorant about them. So the only viable description of uncertainty that probability can have is as a description of ignorance rather than some description of randomness. De Finetti never actually worked with quantum physics, might have changed his mind. So on the other side, you had the objective Bayesians. So the objective Bayesians were receptive to a different part of this critique of Bayesian statistics. By the way, don't be fooled by the name. They still use subjective probability. All Bayesians do. But objective Bayesians said, all right, how do I come up with a procedure that's going to give the same answer no matter who uses it? How do I just let the data speak instead of worrying about different people's prior knowledge? And so they invested a lot of time and effort in coming up with what are called non-informative priors. And these are priors that are expressive of ignorance in some mathematically defined way. So for example, that smiley face prior I showed you a few slides ago, that is a non-informative prior, and it's actually less likely to bias your data than a flat uniform prior is. Every time somebody just uses a finite uniform prior, then an objective Bayesian sheds a single tear. There are more rigorous ways of expressing that concept. Some objective Bayesians take it a step farther in the objective stage, where they will actually calculate the frequentist properties of a Bayesian procedure. So remember that Jeffreys prior-based credible interval that I calculated for the probability of rolling a 1? It has a 95% subjective probability of containing my parameter value. That's great. It's also a 95% confidence interval, which means they've tested it using simulation, and they have found that in 95% of cases where you do a random experiment and you follow that procedure, it will capture the real parameter value. So this is basically saying to the practitioner, okay, you're not quite so comfortable with subjective probability as we are. You don't have to be. This procedure is going to work under the objective probability framework as well. And you can guess what the subjective Bayesians thought of that. There are other styles of Bayesians as well. For example, the empirical Bayesians, they use their data to inform their prior, which, depending on which of those gentlemen you ask, is either slightly cheating or a step away from human sacrifice. Something that I hope you've picked up on from the way I've been describing statisticians in this talk is that we take the interpretation of probability very, very seriously, because we have to. Statisticians deliver probabilistic products. Anytime you get a statistical interval or a result of a statistical hypothesis test, that is either explicitly a probability or a function of a probability. If you don't start with a probability distribution that means something and then maintain that meaning very carefully through your various mathematical permutations, then you end up with a number at the end which you can't use because you don't know what it represents, what it stands for. So this is why this is a big deal to statisticians, be they Bayesian or Frequentist. Not everyone uses probability that way. Some people use probability as an intermediate step in some other procedure. And in that case, since the probability is a means to an end, they are a little bit less sensitive to maintaining a really good interpretation for that probability. One of the examples of that is Bayesian search. And one of the best examples and one of the earliest examples I have of Bayesian search is the search for the USS Scorpion. So the Scorpion was a skipjack-class nuclear submarine that was lost with all 99 crew aboard on May 22nd, 1968. And when I say that she was lost, this was not just a tragedy, which of course it was. It also presented a very practical problem because the last known contact with the Scorpion was on May 21st, and she was off the coast of Europe. She was supposed to return to her home port in Norfolk, Virginia on May 27th, but she never appeared, which means that somewhere in the Atlantic Ocean, you have a missing submarine, and needle in a haystack has got nothing on that. So eventually, the US Navy was able to use acoustic signals, which they believe are from the accident where Scorpion sank, to localize somewhat the location of the wreck of the submarine. However, their search box was still well over 100 square miles. It was 400 miles from land, and it was a part of the ocean that was up to 2 miles deep. So this is a non-trivial problem. On top of that, they have other sources of uncertainty. They couldn't precisely locate the search ship that they were using to check the ocean floor for Scorpion. They didn't have GPS. They had both false positive and false negative probabilities for the sensors that they were using to sweep the ocean floor. And they could not figure out how do we fold together all of this information to try and conduct this search in a credible way. And they went to a man named Dr. John Craven, who was a mathematician who was very interested in Bayesian search. And Craven and his team said, all right, well, first of all, we need a prior distribution. And they came up with one. They were working with a number of experts from the Navy about where might an incident have taken place, what would the heading, the speed, the depth of the Scorpion have been, what were scenarios that might have caused the Scorpion to sink, and they rolled all of this together into a probabilistic prior. They sampled that prior, and they fed it through a simulation to say, if the accident had occurred in this way, where would the wreckage of the Scorpion now be found? And the Navy had divided up their search box into grid squares, and the prior is actually the count of the number of times the simulation placed the wreckage in one particular square, just divided by the total number of 10,000 simulations. On top of this, Craven's team came up with an update procedure, similar to what we saw with the table Bocce example, where based on the false negative and false positive probabilities for the various sensors they were using to try and find the wreckage, they could update this probability distribution based on where they'd already looked. Now, it took a little bit of time to fold all of this together, but eventually they appeared literally on the search ship in August of 1968 with this prior and this update procedure, and you will all be shocked to hear that the Navy did not let the math people drive. This is because they thought they'd already found the Scorpion. They had had a magnetometer contact at that location right there, and they were now searching repeatedly this grid box, and they were not able to get a photograph of the wreckage with their camera, which was their sort of gold standard of their search sensors. And so the first job that the mathematicians had was a futility calculation, was basically saying, based on our false negative and false positive probabilities, when have we searched here long enough that we would have seen the Scorpion if she were there? And eventually they concluded that they would have had an 80% chance of seeing the ship if she'd actually been there, so they moved on from that search box, concluding it had been a false positive. Eventually, they did let the mathematicians drive, and they promptly went to that darkest blue box up in the middle, and they searched and searched and searched, and they didn't find anything. And they concluded that they needed to refine their model a little bit, they needed to integrate their location uncertainty, they needed to understand their sensors a little bit better with false positives and false negatives, and they went out on a calibration cruise to better understand their mathematical model, and promptly found the submarine. Such is life. So when I say that this was not an exquisite Bayesian model, what do I mean? Well, the biggest problem with it is this discretization of their probability distribution. And the problem with discretizing your distributions is you can bias your results depending on where you draw those boundaries. And you can actually see where that happened here. Scorpion is 300 yards away from the highest probability box. Each of these boxes is about 3/4 of a mile square. If they had drawn their boxes in a different place, they might have found the ship sooner. So that's my warning about discretizing your distribution, but I'm not saying that they did anything wrong for two reasons. Number one, they found the submarine, and they found it faster than they would have if they had not been using Bayesian methods, so we have to call it a success on that front. And second of all, they did not have a choice. They were on a ship in the middle of the ocean, literally working 24-hour shifts. They had to be able to update this distribution in real time. And that means they needed a distribution they could actually compute with. So if we had used a fully rigorous, continuous Bayesian distribution, they almost certainly would not have been able to update in time. In fact, at this time, they probably wouldn't have been able to work with it at all. So they took the mathematical shortcuts that were necessary to be able to work on this problem. And if you are ever asked to do a probability calculation in the 1960s on a ship in the middle of the ocean, you can take shortcuts too. Otherwise, consider not doing it that way. So I have just alluded to an issue that I think some of you are probably wondering about, which is, why do people think Bayesian statistics is new? It's not. It's hundreds of years old. In fact, it's older than its most popular competitor. So why is it you didn't start hearing about it until fairly recently? And the answer is computational. Remember that that constant of integration that I kept kind of glossing over earlier on in the slides, that's actually a huge problem. It turns out you cannot arbitrarily combine a prior distribution with a likelihood and expect to be able to compute with it. You almost certainly can't write it in closed form. And Bayesian inference, for hundreds of years, was limited to this very small family of priors and likelihoods that were compatible and computable. There's a reason you saw the beta binomial model 3 times during this talk. So that changed in 1990 with the publication of a paper by Gelfand and Smith on something called Markov chain Monte Carlo. What MCMC lets you do is sample from a distribution even if you don't know the constant of integration. So now the Bayesians can go to town. They can put together any prior and any likelihood that they want. They can sample from it, they can do numerical integration, and they can do inference on those samples of the population. And this is what caused the Bayesian Renaissance. It was the combination of the availability of these algorithms with the availability of increasingly sophisticated computing hardware. And this is what allows for the use of very elaborate hierarchical style Bayesian models today. National Laboratory connection, the MCMC algorithm is a direct line descendant of something called the Metropolis algorithm that came out of Los Alamos in the 1950s, and our old friend Edward Teller was a co-author on that paper. So, prepare yourselves. It's time for the big reveal. What kind of statistician am I? I am all of the above. I have used every style of inference that is presented in this talk. In full honesty, I was raised frequentist, as so many of us are, and to this day, my instinctive understanding of probability is a frequentist understanding. It's probability as a representation of random events. That said, when frequentist inference can't do something I want to do, I go Bayesian. A good example is my dissertation is actually a set of Bayesian models, and one of them is a very elaborate model over protein folds, where it's probabilistic distribution over the structures that proteins can take. And this model draws information from adjacent regions of the same protein, from families of closely related proteins. When that is not available, the prior goes out farther afield and draws information from a broad class of general proteins. I could never have written that model in a frequentist way. So my take on inference is that if it makes sense to you for your problem, and if you are upfront about why you made the modeling decisions that you made, it's all good. And if somebody disagrees with you, that's fine. They can analyze it their way. Maybe they get the same answer. Maybe they don't. And then you get to learn something. So I've mentioned that the frequentists are better at marketing than the Bayesians. I meet a lot of people who are hesitant about Bayesian inference because of the word subjective in terms of subjective probability. Subjective does not mean arbitrary. Subjective does not mean non-rigorous. It means dependent on human judgment. And everything we do in science is dependent on human judgment. When we decide what hypotheses we're going to test, how we set up our experiments, how we're going to take measurements, when you do your statistical analysis, your choice of likelihood is subjective. So if you introduce a well-considered prior distribution, that's not going to somehow contaminate your beautiful objective experiment. In fact, sometimes clinging to mathematical objectivity can lead you down the wrong path. And I have an all-frequentist example for you. Remember Ron Fisher? He was one of the early advocates for the use of randomization in experiment. And one of the reasons for that is that if you use randomized controlled experiments, that can help you establish causality in a mathematically rigorous way. In fact, it's probably the only thing that can. The early evidence linking smoking with lung cancer was all based on observational studies. So Ron Fisher went on world tour, literally saying, correlation is not causation. The evidence is just as consistent with cancer causing smoking as smoking causing cancer. Now, on the one hand, he's right on the math. He's wrong on everything else. When you think about it, they never are going to do that randomized controlled study for smoking. And they never did it. So what they did instead to establish causality was look at the weight of the evidence, all of the different observational studies, the fact that people tend to start smoking before they get cancer, which is subjective, studies in animals, which might have been randomized, chemical analysis of cigarette smoke, and you put all of that evidence together, and you use human judgment to say, yes, smoking causes cancer, not the other way around. It's not justified by objective probability, but it's still the right answer. So, What have we learned today? Well, you have learned that statisticians use probability to describe uncertainty, and that we don't always agree as to how that should be done. You have learned that it's not just about the Bayesians versus the Frequentists. We also have the Frequentists versus the Frequentists and the Bayesians versus the Bayesians in a giant statistical scrum. John Tukey once said the collective noun for a group of statisticians is a quarrel. So what I hope that you take away from this is a better foundation for your understanding of not just Bayesian statistics, but all statistics. There's really only two pieces up here that feed into inferential statistics. One is mathematical probability, and the second is the application of mathematical probability to real-world problems. Neither of those is trivial. I can't teach you how to be an expert in that in an hour, but it's a lot easier to build an understanding when you understand what you're building towards. So again, this gives you, I hope, a better way to approach statistical methodology and to approach ways to increase your understanding of statistical methodology. So assuming you're not now just going to take a timeout of 2 to 5 years while you just study probability intensively before you encounter statistics again, please don't hesitate to reach out. If you're at the laboratory, you can call me. You can call the Statistical Consulting Service. If you're outside the laboratory, then don't hesitate to contact a statistician at your own institution or at a university. I play up the stroppiness of statisticians in this talk because it's funny. But in my experience, statisticians are very friendly, very collaborative people who just like to argue for fun. So on that note, I hope that you have learned something today that will help you in your future encounters with statistics, and thank you all so much for your time.